All right, with that, let's get started. Once again, welcome to today's presentation. Today we're going to be talking about S-Concrete. The title of the presentation is Reinforced Concrete Design Without Limits. And this is going to be a bit of an introduction to S-Concrete and S-Line, which some of you may or may not have heard of before. And I really wanted to start off by perhaps introducing S-Concrete for cross-section design. So reinforced cross-section design of beams, columns, and walls. We'll talk about some of the workflows, some of the different applications perhaps, and the outputs that you get out of the software as well. And then we're going to transition into S-Line, which for all intents and purposes can be thought of as under the umbrella of S-Concrete as well. It's for continuous concrete beam design. And the reason I say that last statement is that if you own S-Concrete, you also own S-Line. Whether you use it or not, it's available for you to use. And we certainly want to make sure that you're aware of all the different tools that you have access to. So we're going to be talking about that as well. You'll be pleased to know that it's developed from the same family that developed S-Concrete. So it has a very similar look and feel with some different features which I think offer a lot of potential and capability to our users. Now, my name is Matt. I'll be leading today's presentation. There are also a couple of us that will answer questions along the way. If we can't get to your questions during the session, we'll do our best to respond to afterwards via email in the coming days. So with that said, let's just jump into the presentation now. And we're going to start off again by talking about our reinforced concrete section design in S-Concrete. If you haven't used it before, you'll notice that it's a powerful yet intuitive interface that allows you to code check and perform designs of reinforced concrete beam, column, and wall sections. So it is specifically a section designer. It supports a variety of different international design codes. And I think what's really valued out of this, not only is the interface being intuitive, but also the ability to handle a large amount of data. We have users that will send tens of thousands of different loading conditions into S-Concrete, and it will crunch those results and spit out the reports, which are detailed and transparent, and give them all the information that they would need that they may not necessarily get out of competitive solutions. And this is a really great tool for quick, detailed evaluation of reinforced concrete sections, one section at a time. You will hear later on in the presentation, we have a workflow for kind of larger scale applications, whether that's in a batch operation or with our multi-store designer workflow. But really, I would say that this is a very practical and powerful tool for medium to and small size concrete structures. And I mentioned earlier the different design codes that we do support. So I've tried to map it out here as best as possible with help from our software development team. So S-Concrete has, in the last few years, it greatly expanded the number of design codes that are supported. I'm based in Canada, so we do have the Canadian codes. The CSA A2319 is the latest in S-Concrete, but we are working on the A23.324 code, which is already in our foundation design software as Foundation, and it should be in S-Concrete in not too much longer. The same goes for our American users. So we support ACI 318.19 and older versions, as well as the ACI 440.11.22 code for GFRP reinforced concrete. And we're working on the ACI 318.24 code as well. Across the ocean, we have Eurocode annexes for the UK, Germany, Spain, and France. We also support the Korean concrete design code, the Indian concrete design code, and some Singapore codes, as well as the British standards. And you may be wondering, if you've never seen S-Concrete before, well, what is the workflow? And I suppose it will depend on your specific application. So this is very high level, but how we typically see this is you will first perform a structural analysis. And the tool to perform structural analysis is not S-Concrete. It's not an analysis tool, it is a design tool. But let's say you're using S-Frame or maybe ETABS or some other application that you could perform structural analysis and get the forces, moments, and so on your elements. You can then export that information into S-Concrete. And that export can be done in different ways. Like I mentioned, we do have a multi-store designer workflow that I'll just allude to a little bit later on. We're going to have another webinar on that later this month as well. But the beauty of S-Concrete is that its loads import can be done just by simply copying and pasting spreadsheet data So if you can export to Excel, or you have data in some sort of tabular format, you can get that data in this as concrete, no problem. And those demands will be in the form of factored load cases, and you can have up to 32,000 different factored load cases per section, and it can crunch all that data and perform for you the design checks on all of those different load cases. Once you get those demands in there, you want to define your section details, and that could be, sizing your elements, the dimensions of your actual section itself, perhaps the placement of reinforcements, and plenty of other details that go into the concrete design. And then you want to be able to review the results. So S-Concrete is perhaps unique in the sense that you get instantaneous feedback on your design calculations. So when you, for example, add a new load, or maybe increase the amount of rebar that you have in a zone or within your column, for example, that will instantly reflect in the utilization ratios that are shown in the software. And so it gives you the ability to perform sensitivity analysis and see what impact a specific change might have on your design. And it makes it very easy to perform design refinement as well. We have automated tools to do this, and I know a lot of our users will kind of start with that, but you can do this the manual way as well, and it's very quick to get that outcome that you're looking for. So this involves an iterative process. You might have to cycle back between steps 3 and 4 a few times, but once you're satisfied with your results, you can then print your design report and pass that along to whoever might need that information down the road. And these design reports are prized because they are transparent, they're detailed, they include all the intermediate values that you would need to understand the results that went into S-Concrete's output, as well as clause references for any code violations that you might have. And to really illustrate this, I think it's best presented in a presentation like a live demo. So I've got S-Concrete open here, and I'm currently using the ACI code for this example, although like I mentioned, you can set up for a number of different international design codes. And when I'm starting off with a new section, I like to start off with the edit section dialog. So I'm just going to open this up here, and you can see we specified the dimensions, our design codes, our material properties, and so on. I'm not going to play around with these parameters for now, but I just want to show you what's already in there. We also have under the edit menu our loads, which I talked about a little bit already. So in this example, I only have 8 different factored loading conditions. These are just the defaults that came with S-Concrete, but of course you can enter your own data, you can copy and paste from other applications. If you're running an SRAM analysis, there's utilities to bring in element loads directly into S-Concrete, as well as from other software as well. And you can see here, I've got a little schematic that describes each one of these load types that we have. So we have axial load, we have torsion, we have biaxial shear and moment. And each one of these corresponds to one of these arrows or double arrows. So we know which direction is positive, which direction is negative, and which axis corresponds to what type of load. So S-Concrete is going to look at all these different loading conditions. It's going to look at which ones might cause the highest demands for specific aspects of our design. Maybe one load combination or case will cause a higher axial demand, where a completely separate one will cause a higher shear in the weak axis demand, for example. And it can handle all that information. And what we're getting out of S-Concrete now is, with this 28 by 20 inch beam, I'm getting these utilization ratios. So I like to think of this little status indicator at the top as a stoplight, just like you would when you're driving a car. You have 3 different colors. We have 2 present at the moment, but we have green, which is good. We have yellow, which means you should use caution. There's something that you should be aware of, and you can decide whether you want to proceed or not. And then there's red, indicating that there's a failing code check, and you need to be able to rectify that in order to meet the demands of the code. And as you can see in this example, I have an overall status on the left-hand side that's saying it's unacceptable. I have a shear and torsion utilization. It's showing me I'm using about 31% of my shear capacity, and I have an axial load and moment utilization, which in this case indicates here that I have greatly exceeded the capacity of my section for axial load and moment. And if we look at our reinforcement, you can see that I've got 2 longitudinal bars at the top. I've got 2 longitudinal bars at the bottom. And these little icons on the side indicate the size of the bars. So I have number 8 bars at the top and bottom. I have number 4 stirrups at 8 inch spacing, which are currently open. and I have some face steel, 4 number 5-inch, or number 5 bars rather, as well. And these can be actually specified under the Edit Reinforcing dialog. We can go in here and we can define the different types of bars that we have. So right now it's showing me a table for top and bottom bars with up to 5 layers. I have my stirrups in the bottom left and my face steel in the bottom right. One thing I'm just going to kind of illustrate here is if we wanted to increase the number of bars, for example, in the top or bottom, we could go here and we could increase, for example, I want to say rather than 2, maybe I have 4 number 8 bars. I'm going to enter that here. For some reason, my number pad wasn't recognizing that. So I'm going to say 4 number 8 bars on the top and on the bottom. And perhaps I'll also close my stirrups as well. So I've got these number 4 stirrups. I'm going to close them. And I'm going to click OK. And I just want you to pay attention to these utilization ratios at the top of the screen, where I click OK. And you can see here that, first of all, my display of my section has changed. I now have 4 bars on the top and bottom. And I also have my closed stirrups. And when I look at my utilization ratios, well, it's still failing. But I have this shear and torsion utilization has dropped from about 31% to 25%. My axial load versus moment utilization has dropped from about 2.3 to 1.4. Now I could continue increasing this. I could go back into the Edit Reinforcing dialog, and this is just one way that we could increase this. And here I could say I want maybe 5 number 8s or 6 number 8s, or maybe I want another layer. I could do that as well. And you'll notice that we've actually split the inputs here. So you can have different bar sizes within the same layer if you wanted to. But for this example here, let me just go with 2 number 8s and layer 2 on the top, 2 number 8s and layer 2 on the bottom. Click OK. And you can see now we're getting even closer. And it's up to us to decide, okay, well, what's going on in my section? And something that I haven't really addressed yet is we're looking at these stoplights as kind of our guiding light, our guiding principle. But there is more detail behind this design as well. I can go into the results menu and I can click on report. And under report here, if I just drag this over, you can see that we're getting a report that documents our current state of the design. And this is showing me, again, the summary of the design checks, the design codes that I'm using, the material and section properties, my rebar information. So it's checking not only for strength, but it's checking, am I meeting my minimum and maximum steel area requirements for the top and bottom bars. And you'll notice anywhere that I have a violation of the code is going to highlight in yellow or red, and it's going to indicate a message. So I'm going to just scroll through the whole thing here, and I can see, well, I still just have that one message. And it's showing me axial load and moment utilization equals or exceeds maximum according to clauses 22.2 and 22.4 or 11.5.3 of ACI 318. So I can scroll up here and I can see this is where it's governing load case number 3, this one right here. And you can see I have a fairly high moment, but I also have some other forces that are perhaps contributing to this. And what I'm noticing is the governing load case utilizations. It's showing me my capacity of 75 kips in compression. My compression capacity is much higher than that. And this is my moment demand, 415 kip foot essentially. And my moment capacity is actually just under 400. So I need to bring that capacity up in order to meet this demand, so my utilization is less than 1. And that's where we can actually use some of S-Concrete's flexibility within the interface. So obviously I could go into the Edit Reinforcing dialog and I could make that change there. But we can also take advantage of the hotkeys in S-Concrete, and the interface itself lends itself nicely to making these variations. So I know I have 6 total number 8 bars in 2 layers on the top and bottom. And maybe I want to actually increase that bar size. So I can go from a number 8, I can actually see here, I've got this number 8 shown here. And I can left click on my mouse, or with my mouse rather. And when I left click, it upsizes that bar from a number 8 to a number 9. And you'll notice when I made that change, I'm now passing this code check. All of my statuses are green. I can go down a size again by right clicking. So you can think of this paradigm as left clicking, add steel, right clicking, remove steel. And I could do the same thing with the number of bars. So rather than maybe having 4 bars on the bottom layer, or top layer rather, I could say, let's go with 5 bars. And we can quickly study what impact each one of these changes will have on my design and which one might be most efficient for my application. So we can see those utilizations in real time and make those changes perhaps more effectively. And of course, once we're done, we can go to the results report and we can spit out a nice report that is going to show us all of our code checks are passing. Now it's up to us if we want to say that 93% utilization is acceptable, but I'm, for this example, just looking to keep basically all these lights green, so to speak. And we can also see similar bits of information for our shear utilization, all the different shear parameters that go into calculating that. Our stirrup requirements are satisfied. Crack control for our bottom bars and so on are also satisfied here. So we're good to go. Now we don't just support beams. This is a rectangular beam. We also do L beams and T beams, but I'm actually going to move on here and I'm going to switch to a rectangular column. And you can see here with this rectangular column, it's just loaded up the default column, and we have a 22-inch by 18-inch column. And this is actually using the exact same demand forces. I haven't created a new model, but obviously if I were to design a column, I would want to import those loads. But if we just review the loads again, I can go to Edit, Loads, and I can see the schematic that describes the orientation of each one of these loads. So we just want to be aware of this when we're bringing data in from another source. And under the Edit Section dialog, here we can go in and we can see whether we want to add, for example, a hole to our section. Maybe we'll want to have a different design code. Perhaps I want to switch to the Canadian code or the European code. That's all up to us what we decide to do. And finally, we can control our reinforcing just like we did for beams. We can control it through the Edit Reinforcing dialog. Here's where we could configure, the splices between our vertical bars, the number of face and row bars that we have, as well as the configuration of our horizontal bars. So if we had a circular column, we might not want to have a rectangular configuration of our longitudinal bars. We might want that to be circular or spiral. And for this example here, you can see that we've got an 18-inch by 22-inch column. Let me actually make this a little bit smaller. So I'll make it 20 by 18-inch, and you can see our utilization shown here. We see our row steel area. I have 16 number 8 bars. And if I go to the results report, I can see that we are failing some of our code checks. So I have an overall status of unacceptable. My N versus M utilization is 1.289. And continuing to scroll down here, I can see where that failing utilization is. But I also have some issues with tie spacing for shear and torsion, vertical bar spacing, and so on. So I have a couple different clauses that are being violated. And those are indicated here in my report. Now, just like I did with beams, I could go through this and I could configure the design by using these hotkeys. And I could say, maybe I want additional bars, 18 number 8 bars, for example. And maybe that will get me slightly closer to my passing code checks, although I might have some issues with bar spacing. You will notice actually when we change our number of longitudinal bars, it's going to adjust our stirrup layouts according to the design code requirements. But I'm actually going to take a different path here, and I'm going to go to the Run menu, and I'm going to set up an auto design. So I'm going to go with Design Constraints. And here, we can set up some parameters to be considered for our automatic design. So for example, right now we have a 20 by 18-inch design, space, I guess you could say. And perhaps I want to freeze this width at 18 inches, but the depth I can adjust a little bit. Perhaps I have a little bit of architectural leeway there. And we can also control the reinforcing bars that are used, so I can set a range of bar sizes that I can consider, or I can freeze those parameters again, like I mentioned. I'm going to just click OK with these inputs, and now I can go to the results menu, Run menu, and go to Automated Design. And I'm just going to put this at the top of the screen here. You can see all the different parameters that basically describe that column. And I'm going to automatically step through a bunch of iterations with this. So I'll click Auto. And you can see here, I've let S Concrete basically take the wheel and come up with a kind of an iterative solution that's going to work for my particular application. Now, in this scenario, we have frozen some of the parameters, like the width I kept at 18 inches, but the depth I allowed it to vary, so it went from 20 inches to 26 inches. It was able to reduce the number of vertical bars, but it increased the bar size. And you can see the steel ratio actually increased from 3.51 to 4%. Now, this isn't necessarily going to come up with a perfect solution for us, but it can get us in the right ballpark, and we can tweak it beyond that. So it's helpful if you perhaps want to approach the design in a uncharted territory and you want to get a bit of inspiration in terms of where you want to head with that design. Now we see here that we're passing out the code checks. Another result that's available to us here is the N versus M diagram. So N versus M diagrams can be produced for our section at different theta angles. And we can see here the governing theta angle that's being used with our moment and axial load shown here at 75 degrees. I can switch this to any different theta angle, and I can see the results at that location. So I'm just going to look here. If I right-click on this point, I can look at the normal envelope, for example, and I can see the moment, the axial load, the compressive block depth, the effective depth, the amount of steel that's in tension, as well as the strain in the neutral axis angle. So we can get quite a bit of information from this type of output. And those can be included in a report as well. Now the last section type that I want to introduce is the wall sections. So we have here 4 different shapes of walls. We have I-shaped walls, which can also be rectangular walls if we wanted to basically keep the same thickness throughout. I have C-shaped walls, T-shaped, and L-shaped walls as well. And for each one of these, we have some different nuances that are perhaps unique to walls that we don't have in other sections. So I'll just use this L-shaped wall as an example for now. By now, we're probably familiar with the loads that we have input in this example, because we're just using the same loads for each section that I have. But let me just introduce here under the Edit Loads dialog. Just bring this over from my other screen here. You can see here that it's showing us a schematic for our sectional loads. So we have 2 different types of loads. We have sectional loads, and then we have panel loads. So sectional loads are applied at the center of gravity of our cross-section, and they are distributed throughout our section according to the relative stiffnesses and so on, and in this case, areas of concrete that are used. I also have panel loads, which allows me to induce specific loads into my panels. This can be helpful if we wanted to design for shear, for example, in a panel, and we wanted to say, for sure, we have X amount of shear in this panel, X amount of shear in this panel. And as concrete, we'll look at both and decide which one is governing for each particular check. We can also control the load type. So this can be a seismic load type, for example, or it can be a wind load type, or another load type if that were the case. Under Edit Section, here we have all of our dimensions that we can configure. We can also control the seismic design parameters for this particular section to decide how the anchorage and ductility requirements are going to be determined based off of these inputs. And lastly, under the Edit Reinforcing dialog, you can see here that we have inputs for both zone and panel reinforcement. So for an L-shaped wall, we have 3 different zones: Zone A, which is right here, Zone B, and Zone C. And we can control those independently of one another and concentrate our reinforcement in those zones. As for our panels, we have 2 panels, panel 1 and panel 2. Here we can control how many curtains of rebar we have, the bar size, the hooks that are going into our zones. Again, the type of hooks that we're using can be important depending on things like seismic parameters and so on. So that's something that we can certainly control. And I'll just click OK. And we'll see our utilization shown just like we have before. So in this case, now I have passing strength checks, as I call them. My shear torsion and axial load versus moment utilizations are all passing. I can go into the results and see the N versus M diagram. And I can see either on a panel by panel basis or an entire cross-section basis how each one of my load cases is kind of falling within this envelope for different utilizations or different loading conditions and so on, different theta angles. And I do want to study why this status is a warning when my strength checks are passing. So I can go to the results report, and here I can see that I have, if I scroll down through the list, and maybe I'll go right to the bottom, I have 3 different messages. I have panel vertical steel ratio doesn't meet the minimum, panel horizontal steel ratio doesn't meet the minimum, and the zone center to center vertical bar spacing doesn't meet the minimum required. And I can see more information related to each one of these. So for zones A and B, I have, in this case here, it looks like my my issue is with the bar spacing and the maximum bar spacing that I'm allowing. I have some issues with panel reinforcement, where in this case here, it looks like I'm actually under the minimum for my panel number 2. So I would need to consider those and perhaps revise them. And we can see more information related to these hotkeys, and I can see my bar size, the number of bars that I have in the vertical and horizontal directions, and I can increase that spacing or decrease it to my liking. So I can left click and bring that bar spacing down, for example, and I can do the same thing with my zones. Now, since we've seen this process a few times already, I'm not going to go through that same workflow. I do want to mention here that all the sections I've been working on, I've kind of been treating them one section at a time, where I have those loads already input and I'm designing those sections kind of all at once, one at a time rather. If we did have a lot of sections that were already created for us, we can actually run a batch process where we place all the sections in a file. We run this batch processing reporting utility, and it will allow us to basically perform a design or a design verification, for example, on all the sections all at once and generate a nice consolidated design report rather than one section at a time. So let me just jump back into my slides here. And kind of an extension to what I was saying earlier about having a lot of data that you might need to process. I mentioned the batch processing where you would create those files yourself and basically press a button to let S-Concrete perform the design checks on all of them and output results in a single consolidated report. Another application might be if we had an analysis done. Now this analysis could be done in SRAM, it could be done in eTabs, and we're working on other applications like STAD and MIDAS as well, where you can perform your structural analysis on a 3D concrete structure. You'll know all of the element sizes in your analysis model. You'll know the forces on those elements. You'll know whereabouts on the structure they exist. And you can export that to an Access database and then bring that data into the multi-story designer, which is basically a utility within S-Concrete that can handle lots of different cross sections that were exported from that analysis software. It'll perform preliminary design reports, design checks rather, and allow you to modify the design en masse rather than one section at a time. And then it's going to produce all those S-Concrete files for you, which we found is a fairly time-intensive process for some of these manual workflows where they have to produce lots of different S-Concrete files with all the different loading conditions and reinforcement and so on. So it can do that for you automatically based off of the limited input that you needed to make in the multi-story designer. Then you're going to get all your design reports, and that can be an iterative process as well. So you can go back and you can modify your design all within this interface. So you have a lot of control over either one section at a time or several sections, and basically driving the S-Concrete interface through them and the design engine. Now, if you're curious about this, we do have a webinar coming up, I believe in 2 weeks. I'll have to double check my notes. It's at the back of my slide deck. And we're going to talk more about that as well. That's called the multi-story design. But I am going to actually switch gears now and look at continuous concrete beam design. And as I mentioned at the very start, this is available in a tool called S-Line. But for all intents and purposes, I'm calling this S-Concrete because it's available to anybody that has S-Concrete. It's built from the same kind of platform and team that developed S-Concrete. So what S-Line is a standalone product that analyzes, designs, and details continuous reinforced concrete beams. And it runs various code checks, and it supports automated design. Now, there are multiple design codes available, just like we saw within S-Concrete to choose from. And there are various beam sections available as well. And it supports the very handy visual editor that we've seen in S-Concrete, where you can alter geometry, reinforcements, quantities of bars, and so on. As well, it includes several features to assist with longitudinal beam modeling. And just like the rest of our products, we have the automatic report generation, which looks and feels very similar to S-Concrete, to document your results. But S-Line can also export DXF files in AutoCAD and documents in Microsoft Word, which S-Concrete can do as well. And like I mentioned, this is available with S-Concrete and the structural engineer suites on Altair licensing. So if you have S Concrete, you have S-Line already. So let's just quickly look into S Concrete or S-Line as well. Here I'm mixing up the names. And this is an example in S-Line that I've got loaded up here. You can see here we've got a continuous beam, effectively, that's supported in a couple different locations. So we have a column underneath this left-hand side, as well as here we have a column on top and on bottom. We have a girder, which will basically act like a pin, so to speak. And then we have columns on the top and bottom on the right-hand side. And you'll notice that the beam profile varies throughout the length of this beam. We also have different spans, and we can actually vary that. Just like in S Concrete, we can left-click and drag our beam spans and modify those to our liking. Same thing with the depths. And when driving S-Line, it's very common, at least for me, to suggest that you should start in the Edit menu and just kind of work your way down this list. So I'm going to start with the Edit General Information and just introduce what we have here. So I'm using the CSA 2019 code. We can see inputs for our concrete strength, our steel strength, and so on. I'm just going to stick with what we have for now. And continue down the list. Here we have member configuration. So this allows us to control for each bay in our model. So you have 3 bays, 1, 2, 3. We have a tab for each bay. So we have our cross-section types, the dimensions that are being used, and effective section property modifiers as well. And it's available again for each different cross-section and each different bay that we have in our model. Continuing on here, we can go to Edit Reinforcing Styles, and this is where we specify kind of our high-level reinforcement inputs. So we can control the top bars, the bottom bars, and the miscellaneous bars in different tabs. And so if I look at the top bars, for example, we have different styles. So this is going to be the style that's going to initialize our beam width if we don't make any changes. I can say, let's go with top bar style number 2, which will basically have a lap here at the center of the top of the span here. And we can do the same thing for our bottom bars and modify those with different styles that we might want to use. So I'm just going to click OK. When we do this, it's going to apply those reinforcing styles, and it's going to initialize all this data with some default parameters that we can get started with. So we can start to see here are our stirrups. This will show us basically our stirrup spacing in different beam zones. So whether it's in the center, just to the left or right of center, getting closer to our supports, we'll have different shear, so naturally different stirrup layouts as well. We also have our longitudinal bars, which are shown here, the bar sizes, and we can actually click and drag these bars to extend them deeper into the beam if we wanted to. And if we really wanted a lot of control over our beam and our reinforcement, we can go into the member reinforcing dialog, which is a bit of an eyesore, I'll admit it, but it has a lot of information. So again, for each bay that we have in our beam, this will basically show us all the inputs that we have for our reinforcement in our beam. So we have A bars, B bars, and C bars, which are longitudinal top left, top middle, and top right bars. And those all correspond to this little schematic here that you can see. So it may be a scenario that we don't have, for example, B bars, because our A bars are extending into the B zone, into the middle of our beam. And that's what we have here, actually. And then we have D bars, E bars, and F bars, which correspond to the same thing, just on the bottom. So here we can see here that we've got, in this case here, I've got 3 bars in the E section. This is the extension to the left and the right. This is the bar size and the hooks that we're using. And we have different layers as well. And I can scroll down, I can see I can also input base steel. I can input my stirrup parameters as well. I'm just going to click OK. And the last few parameters here are member loads, which you can see we can enter in a spreadsheet. So we can have distributed or concentrated vertical or torsional loads. And then finally, our load cases and combinations, which will automatically be set up for pattern loading, but we can make our own custom load combinations as well, and set up our own load combination factors, as well as our service loads, which will be used for things like net long-term deflection and so on. So with that said, let's go ahead and run an analysis in the code check. That's one difference between S-Line and S-Concrete is that S-Line is running an analysis. It has a solver. So I'll click on Analyze and Code Check. I'm going to let it run the analysis here. It's going to generate our diagrams and all of our code check results as well. And you can see here, through pure luck, we got a utilization ratio that seems to be passing for all of our spans, which was not my intention, but it happened to work out that way. But I do have this warning message for each one of my beams. So let's just start by looking at some of our analysis results. I can look at things like, for example, my deflection diagrams. So this is available on a bay-by-bay basis. So this is my first bay here. And we can see we have different load combinations that we can select from. This gray lines will just indicate the different load combinations that exist in our model. And I can see at any point what that deflection might be for the indicated low case or combination that we're looking at. I can also see here things like my moment diagrams, and our moment diagrams will show not only the moment demands throughout the beam, but also the moment capacity envelopes, as you can see here with these blue lines for the negative and positive sides. Same thing goes for shear and for torsion if we have torsion in our beam. And again, available for each one of our cross sections that we have, or beams, our bay sections rather. And if we wanted a more holistic view, I can go to the results report and look at the analysis model. This is actually handy because it allows us to see things like our our actual section properties and material properties used for the analysis model. I can see the assumptions made for all the boundary conditions as well. And I can look at things like my deflections. So I can select which load case or combination I might want to look at. So I'll look at my SLS load combination. And this is showing me how much deflection I'm getting in these beams. This is immediate deflection, but I can also toggle on for these SLS load combinations, my net long-term deflections as well, and see what we're getting there. As well as things like moments, where you can see we do have some moments in our columns that are attracting some of the forces away from the beam, and so on. And finally, we have our results report. So this is what the last part I wanted to just indicate here for you. I can see an overall status of warning despite having slightly passing utilization ratios for my strength checks. And I can scroll down through the report and I can see what the issues might be. So this is showing me for my top bars, my AS minimum, my minimum area steel is just under 1,400 square millimeters at a distance of 6750 millimeters along the length of my beam. And I actually have less than that. I have about 1,100 millimeters squared. So I need to increase that. And it seems like a similar report is showing up here. So again, we have more steel that we need to add to the beam essentially. We're also having issues with our stirrup spacing, where it's showing us that we're basically exceeding our maximum stirrup spacing for each one of these segments. So we have some, I'll call them detailing issues that we need to resolve. And we can do that in a number of different ways. I can, increase the stirrup spacing by simply just left clicking on the spacing here that in this icon for our stirrup spacing here. I can do the same thing for all of these different stirrups as much as I like. I can add more stirrups if I want to as well. The same thing goes for increasing our bar counts or our bar steel areas. I can extend the bar a certain length. I can increase the number of bars that we have. And at any one of these cross sections, I can slide this little cursor over and I can view my section at that location and see exactly how many bars I might have in one of those areas. So I'm not going to go through the whole process of resolving all of these since we do have limited time and we're nearing the end of our webinar here, but I did want to kind of introduce you to the interactive interface, which is very similar to S-Concrete, with the only exception here being that we do have to reanalyze after our changes. So it's maybe not quite as instantaneous of feedback, but still very powerful for continuous beam design, as you can see. So I've resolved perhaps some of those warnings, but not all of them. Now, with that said, let's just go back into our slides here. So I just wanted to kind of wrap this up with a bit of a discussion on kind of the high level points that I made today. I would say that our software has a very low learning curve in order to become productive with our concrete design solutions. And they're great not only for validating that you have a utilization ratio less than 1, but it's going into more detail. It's saying, okay, these are your intermediate values. This is the detailing checks that you might have missed. So maybe your bar spacing isn't adequate, despite the fact that you have enough strength in the section. It will report all that to you to allow you, the engineer, to make perhaps more informed decisions and spend less time trusting the software and more time trusting your engineering judgment. Now, if you do want to learn more, we do have a webinar on the 20th of November on the S-Concrete Multi-Story Designer. It's going to be presented by my colleague, Tyann. We also have training. So we have training on S-Frame and S-Concrete. That's either live or on demand. I don't think we have any more live ones this year, but on-demand training courses are available throughout the year, basically whenever you want them. If you go to Altair 1 and you search for training, you'll find those there. And lastly, our YouTube channel, I've just counted as of earlier today, we have over 350 videos on the S-Frame suite of tools. So if you're curious about S-Concrete, for example, I've got a tutorial video here that I can just bring up. This is what I recommend to a lot of new users of S-Concrete. Check out the S-Concrete tutorial for reinforced concrete design. You'll find this one, as well as third-party tutorials that I think are also very good to really learn the software and become productive. We also put our previous webinars online through that YouTube channel. So if you want to check out another webinar that you might have missed, that's the place to look for it.